All right. Hey, everybody. So I said I would make a video about the Fibonacci numbers for Friday's class, and I'm pretty excited. And so let's share the desktop and see what happens. So I want to talk to you about the Fibonacci numbers, and we've seen them in class on a introduction to counting worksheet. But I want to reintroduce them today in kind of a real life example that I kind of first found out about sometime last summer. So I was reading a book about genetics. It was called the Gold Bug Variations. It was a kind of beautiful work of fiction about music and genetics and math and so many different things. And I learned about how bees reproduce, and it's pretty interesting. And so you've probably heard that there's something called a queen bee. So this is the bee that is responsible for laying eggs and generally kind of producing the next generation of bees. And what can happen is that the queen can give birth to either what's called a worker bee, which is a female who does not become the queen. I guess the queen could give birth to a female that would become a later queen, or the queen could give birth to the male bees, which are called drones. And all of these bees have different roles in the hive. But what's really interesting is that the queen bee can decide to either lay a fertilized egg or an unfertilized one. And so the queen is born with eggs that are unfertilized, and after mating with a male, can decide whether to lay a fertilized egg or an unfertilized egg. And if you remember your basic biology, the way that sexual reproduction works is that you have chromosomes, and you get some from the mother, some from the father, and they combine. And so if you have a fertilized egg, it turns out those are going to have 32 chromosomes. And the unfertilized eggs are going to have 16 chromosomes. Right? And so it so happens that these unfertilized ones, those are the ones that become the males. And the fertilized ones are the ones that become female. Right? And so if you think about what that kind of means, is that the male bees only have one parent. Right? They just have a mother, right? Everything has a mother because it's coming from an egg. But the females have two parents, right? They have a mother and a father, right? They get chromosomes from two different parents. And so if we were to draw a family tree, starting with a male bee, so we start with a drone. Remember, the males only have one parent, right? They're coming from an unfertilized egg. Kind of amazing that this works, but this is how bee genetics go. And then that mother, that female, had two parents, because every female has two parents. And then we go up and we look at, I guess we look at her mother would have two parents, but her father would only have one parent, his mother. Right? And as we keep tracing back through this thing, just kind of look on the left, you just can kind of see how it branches off, right? Every time you have a male, it's going to have only one parent. Every female is going to have two parents. And so if we count how many parents, grandparents, great-grandparents, etc., we get this really cool sequence that starts with our lone drone down at the bottom, and then we have parent, grandparent, two grandparents, three great-grandparents, 5, 8, it's 13. And we get this beautiful sequence, which is called the Fibonacci sequence. And so it's this sequence 1, 1, 2, 3, 5, 8, 13, 21, 34. And it has this beautiful property that to get from any terms in the sequence to the next term, we just add up the most recent term. So if we add 3 and 5, we're going to get to 8. If we add 5 and 8, we're going to get to 13. We add 8 and 13, we're going to get to 21, etc. Right? And so this description, I've read now some more terms on this slide, but this description is describing an infinite family, an infinite list of numbers that just starts with 1, 1. Then you add those to get 2, and then you add 2 and 1 to get 3, and you just continue. And so this is what's called a recursive definition. It lets you find the next term in terms of the previous ones. And just let me just share on Wikipedia here. Fibonacci numbers come up in all sorts of ways. You may have seen something called well, I'll show you in a second. But if you start with 1, 1, and then you kind of fill in that rectangle by putting a square in up here, and then you make a bigger rectangle by putting a square over here. And now if you have these and you want to make one bigger rectangle, well, this is 5 across, so you'd have to have a 5 by 5 square. And if you continue in this pattern, Fibonacci numbers will arise. And it turns out if you draw a nice smooth curve connecting all this stuff, you get a really beautiful spiral. And if you've ever seen nautilus shells occurring in nature, this is a shape that occurs all the time. And so there are many great videos out there on the Fibonacci numbers, lots of really cool geometry, and you know, even just reading the Wikipedia page is pretty interesting. Sometimes people will associate Fibonacci numbers with rabbits, because what you can kind of imagine what happens to a set of rabbits that are mating, and then they're gestating for a month, but then they have babies, and then it takes some while for the babies to have their own babies. And as you go through the process, you get these Fibonacci numbers arising there. And so lots and lots and lots to check out. But in our class, this comes at the point where we've just been doing a lot of counting. We're doing a lot of counting. And one sort of, I don't know if it's really a counting problem, but it's a problem about numbers. And it's, what if I asked you for the 100th Fibonacci term? Okay. And, or what if I asked you for the 1,000,000th term? Right? The 100th term, I bet you could do on paper in, I don't know, an hour or so, right? If I told you I'd give you $1,000, I bet you could figure out the 100th term. It'd be really, really, really big. But you could probably very carefully add up all those numbers. And I asked you for the 1,000,000th term. That would be pretty large, but you could maybe write a computer program to kind of do this stuff. And probably what you would do is just calculate all the terms up to that point, right? So far, I've got, I don't know, a dozen terms or so on the screen, and I could just continue that process. No, not really hard work, but it might be a lot of work to go all the way up to 1,000,000, right? It might take a lot of computer memory, right? And I also might be interested in just kind of jumping directly to that nth term. Do you think there's a way that we could find a formula for that nth term without calculating all of those intermediate terms? Okay. And you may be asking, well, why would we want that? Well, one thing is that if we had a formula, it might give us some insight, right? If we look at that formula, we might say, oh, I see that this is describing the rate of growth. Okay. So for instance, what I've done here, and we're going to explore on Desmos in a moment, but I've plotted the first, it looks like 8 Fibonacci numbers. I don't know if they all fit on this window. It looks like they did. And I've just plotted them 1, 1, 2, 3, 5, etc. And I look at that, and right away, the word exponential comes to mind. This looks like an exponential graph. It looks like things are shooting up. And so right away, that kind of tells me if I wanted a formula for the nth term, I might look for, you know, something like e to the x, or maybe it's 2 to the x, or, you know, something like that. Of course, I meant 2 to the n, because I guess we're using the letter n for our Fibonacci number. And if you go on Wikipedia and you look for this exponential function, just kind of glancing through, Wikipedia will throw these formulas at you. I just want to, let's start at the bottom. There is a formula, right? It tells you that the nth Fibonacci number is equal to this formula. I'm going to focus on this one on the right. It says it's equal to phi to the n, whatever phi is, minus psi to the n. These are just Greek letters. And we divide by the square root of 5. And so what are these numbers? Well, phi is just a number. So they could have written 1.618 to the nth power minus negative 0.618 to the nth power, right? And then divide by square root of 5, right? So it's this kind of crazy formula, but it is exponential, right? We see a number. It's not as nice a number as like e to the x or 2 to the x, right? It happens to be this weird decimal, which is actually called the golden ratio. But it's some number raised to an exponent. And then we have to subtract something else. There's a little adjustment factor we have to do. But what's so cool about this is that somehow the Fibonacci numbers, remember, they're just these numbers, 1, 1, 2, 3, 5, 8. They're all whole numbers. But somehow the formula for it involves the square root of 5. Right? And this has always kind of fascinated me as, I don't know, I thought, why is that true? Right? And so, like, I don't know, I have this question here. Where the heck does this come from? Right? So here I've plugged everything in. I've plugged everything in, and I say, here's what Fn is. The nth Fibonacci number is do 1 plus square root of 5 over 2, raise it to the nth power, and then subtract this other crazy number, and take it to the nth power, and then divide by square root of 5. Right? And so if you're watching this video, we've just kind of seen Fibonacci numbers come up from genetics or rabbits or spirals or things like that. And if you want to keep watching the video, I hope it's out of some sort of curiosity of like, wait a minute, I would have never guessed that that's the formula. What's going on? Why is this happening? And that's what I want to do, right? And so the first thing we should do is just kind of convince ourselves and agree that it works, right? And so like, if this formula is supposed to be right, then apparently if I plug in 8, I'm plugging in 8 for n, so I'm going to do exponent of 8. Then apparently if I plug this in, I'm supposed to get the 8th Fibonacci number. 1, 2, 3, 4, 5, 6, 7. Oh, so 8th Fibonacci number is 21. I put that in a box. And crank it out. Get your calculator, type in all those numbers, and see what you get. You actually are going to get 21, right? And I know I probably wouldn't have done it if I were watching a video myself, but I've got a little formula in here, right? Maybe I'll just kind of copy this. Right? And if you don't believe me, let's just set the exponent to 8. We get 21. And what's the previous Fibonacci number? The previous Fibonacci number was 13. And so why don't I change that to 7 and 7? And sure enough, I get 13. And what happens if I set it to 1? What if I go all the way back to the beginning? What if I plug in 1? If I plug in 1, I get the first Fibonacci number of 1. I plug it into 2, I get 1 again, right? Because the second Fibonacci number is also 1. Remember, it starts with 1, 1. Right? And so for whatever reason, this formula is right. Right? In fact, if I were to graph this function, if I were to type this in, let's see what Desmos does if I try to graph this. Right? It's kind of hard to tell, but it's graphed in red. It's plotted all of these different points. And sure enough, this weird exponential function is going through all of those points. Now, if you're wondering why it's dotted instead of kind of a solid line, the reason for that is that this number over here, 1 minus square root of 5 over 2, is negative. And so if you take a negative number and you raise it to like the 1/2 power, that's like the square root of a negative number. And so the reason that the dots are in here is that this function is not always going to be defined if we're not plugging in whole numbers. But we're just plugging in whole numbers for the Fibonacci number, so there's not an issue at all. So let's go back. Let's go back to our notes. Right? So it seems this formula really, really, really does work. Right? And so in the rest of the video today, I would like us to investigate maybe why this is true, and maybe doing that by thinking, how could anyone ever find this, right? Because it's one thing to say, okay, I have a formula. I believe that I checked a bunch of values. But I want to know, how did someone find it? How did mathematicians ever think that it could be this? Did they just try formulas at random? And I want to show you actually that there's a very reasonable method that will produce exactly this formula. And that's what I want to do next. But I am cooking rice and the rice just beeped. And so I will pause recording and be right back. All right, I am back. So let's do it. Let's do it. Let's see why this formula is true. All right, so I'm going to show you a really cool trick. It seems like it shouldn't do anything, but it actually does so much. So our goal is to study this sequence 1, 1, 2, 3, 5, 8, blah blah blah, and I'm gonna study this same sequence, right? I'm just going to put those numbers in front of things like x, x squared, x cubed, x to the fourth, etc. And the only reason I'm doing that, at least for now, is just to keep track, right? So now we have a handy index that helps us keep track of the term. For instance, I can look straight away and say, oh, because I put an x to the 9th on this, that means this is the 9th Fibonacci number. So that means that 34 is going to be the 9th Fibonacci number. And I can glance right away and say that 5 is the 5th Fibonacci number and 13 is the 7th, etc. Right? And in general, whatever number goes in front of x to the n is going to be the nth Fibonacci number. Okay? So if I'm looking at it and I see something times x to the 97th, whatever number is in front of it, that's got to be the 97th Fibonacci number. And so for those of you who have taken Calc 2, this is what's called a power series. You've probably studied a lot about these, and you've studied things about convergence and maybe Taylor series and stuff like that. But for us, it's just really just a list of numbers as coefficients. And our idea, the idea of this is, can we somehow, you know, if we're looking for the nth Fibonacci number, looking for the 100th Fibonacci number, the millionth Fibonacci number, can I somehow extract that in some different way? Can I somehow do some magic and get a formula, and maybe get that formula with the square root of 5? Well, I don't know. Let's see. Okay. And so let's just look at it. Right. So this is exactly what I had before. Remember, I've got my Fibonacci numbers 1, 1, 2, 3, 5, 8. I'm just going through. And let's just call it S, right? Stands for sum. And what I'm going to do is I'm going to take that sum and I'm going to multiply by x. And so before I advance the slide, I want you to think, what would happen if I took that power series, or think of it as an infinite polynomial if you want, you multiply it by x? Well, I think what it's going to do is going to take this term and it's going to send it to 1x squared. And this is going to become 1x cubed. And that'll be 2x to the 4th. So if I multiply by x, it just shifts everything one step to the right. Right? This 5x to the 5th now becomes 5x to the 6th after I multiply by x. And that was so much fun. Let's multiply by x squared. Right? That should just shift it 2 to the right. Right? So like this 2x cubed, it's going to become 2x to the 5th. Right? So that's super awesome. Right? So I'm kind of multiplying through. And now I'm going to point out something super exciting, is that if I take the top line, S, and then I subtract off the next two lines, right? I take this and I subtract them off. Well, let's see what happens. Well, I don't know. Here I'm going to get 1x minus 0 minus 0. But here I'm going to get x squared minus x squared. And here I'm going to get 2x cubed minus x cubed minus x cubed. That's 0. Those cancel. And here they cancel, right? What's happening is that this 8 is going to, when I subtract 5 and then subtract 3, that's just going to cancel all the way down to 0. And so what this whole thing simplifies down to, this infinite sum, once I do this little magic, it's going to subtract. Once I subtract these things, I'm going to get just 1 times x to the 1st, which is none other than just x. Right? And so this whole thing is equal to x. And now I can factor out an s and try to solve for s. Right? So I just rewrite that. I say that's s times 1 minus x squared. I can now divide both sides. I can solve for x. I guess s must be x over blah, blah, blah. And then that, okay, I guess that means it's equal to this. And so we just did a bunch of algebra. And so if something didn't make sense here, just pause and just kind of just verify the steps. But what we've done is we seem to have shown, we started with this infinite power series here, 1 plus x plus x squared plus 2x cubed, etc. And we did some magic with it. Remember, we called it s, and then we solved for s, and we saw that s was equal to this fraction. Right? And now might be the part where you're saying, okay, I'm a little suspicious. I don't know what's going on. Well, let's see. So here, let's see what I've got down here. Okay. So down here, I've written the start of this power series. Okay. And so I could add one more term and see if that affects the graph. So right now, this is a graph of a degree 9 polynomial. If I add one more term, 55x to the 10th, and then I add the next one, what would the next one be? 89x to the 11th, right? You can see that it's kind of updating the graph. And each time I add like extra terms, it's going to adjust it a little bit. And somehow I claimed that if we do infinitely many, right, if we just kind of do in the limit, then what's going to happen? I claimed that it would be the same as this function here, right? X over 1 minus x squared. And so let's see. So let's take this one away and put this one in. Right? So that's that fraction x over 1 minus x squared. And the question is, do we think it's the same or different from this green, or from this, I guess it's black, from this black graph here? And I hope what you at least kind of see is that they look pretty darn close in a certain range. In fact, if I'm zoomed in enough, these graphs are basically equal to each other. Right? And so what's true is that these two graphs, if I add enough terms and I look on what's called the interval of convergence, these two things are going to be absolutely equal. So it really, really is true that this power series is what's actually called like maybe the Taylor series expansion for this function. Right? And so maybe some of that connects with what you've been doing in Calc 2. If not, I just want you to kind of think that this sum that encodes the Fibonacci numbers is modeled extremely well by this rational function. Okay. And so we're going to use that and see where it takes us. Right? And by the way, everything that I'm doing it can be done completely rigorously. It's not like I keep saying magic, because it does feel like magic, but all of this is legitimate math that we can do. But I'm trying to say that without going into the rigors of how to make everything completely precise, I hope by showing you these graphs, at least it seems convincing, right? And so we're almost there. We're almost done. And so we've got this awesome formula here, right? And the only thing left to do is to say, man, let's study this fraction. Let's see what happens. Okay. And so how can this help us give a formula for the nth Fibonacci number? Okay. And so one tool that we will need is something that I hope you've seen in a calculus class, but if you haven't, I'll just kind of show you why it's true now, is this really kind of cool fact that if I do 1 over 1 minus r, I claim that's the same as 1 plus r squared plus r cubed plus r to the 4th. And again, there's a whole theory of convergence and stuff that we would learn in a calculus class. But for now, to convince you that this is true, let's just cross multiply. Right? What if I just multiplied both sides by 1 minus r? If this were true, that would mean that this cancels out to 1. And let's see, if I cross multiply, well, I guess I do 1 minus r times 1. That's 1 minus r. And then I do 1 minus r times r. Well, I guess that's going to be r minus r squared. And then when I multiply by r cubed, I get these next terms. And you can see these cancellations happening. Right? We get negative r plus r, that's 0. Negative r squared plus r squared, that's 0. And it just continues. So everything winds up canceling except for that 1. And so now I guess if I just divide both sides by 1 minus r, I'll get 1 divided by 1 minus r equals this infinite sum there. And so this fact, this is called a geometric series. And the fact that it converges to or can be represented by 1 over 1 minus r is something that we're going to use to great effect in the rest of today. And so we're going to use it, and we might use it with the letter r. We might use it with the letter x. We might use it with the letter y. We might use it with 3x, right? We could put 3x and 3x squared and 3x cubed, right? We might even use it with rx, right? The point is that the algebra, when we just multiply that through and saw that cancellation, that's going to work whether it's the letter r or the letter x or the letter y, or really anything we plug in, right? So we're going to use this formula, this identity, that helps us turn something that looks like a fraction into something that looks like a sum of a bunch of powers. And for those of you who are kind of wondering what's going to happen, well, the formula we're looking for our Fibonacci numbers is exponential. Right? We're looking for something that has an exponent in it. And here are exponents. Right? And so this slide is somehow the roots of everything that comes to follow. And it's this great idea that you've all done before in your algebra classes. So the very first time that you learned about quadratic polynomials, I bet you learned how to solve for their roots. Right? So probably you would have taken an equation like x squared plus x minus 1 and said, where is it equal to 0? And you learn the quadratic formula. Right? This thing doesn't factor. It would be nice if it did, but it doesn't. And you would find the roots. You would say negative 1 plus or minus square root of 5 over 2. And so I'm going to call one of those roots R1. Very creative, I know. And the other one R2, which is the one with the minus sign. Remember, we've got plus and minus. And another thing we know about quadratics is if their roots are like 2 and 3, then that should mean it factors as x minus 2 times x minus 3, right? And if the roots were 5 and 6, it should be x minus 5, x minus 6. The same thing is true here, right? If the roots are R1 and R2, that this polynomial must factor as x minus the first one times x minus the second one, right? So just because these numbers are decimals, right? 1 point, I don't even know what they are, like 0.608 or something like that. Just because they're decimals doesn't, still have this to be true, okay? Now, I could have written everything that follows. I could have just done it explicitly by putting in these fractions. I hope you'll see why I didn't do that. It gets messy enough as it were. Right? But now we have this thing. So now what am I doing? I'm taking my fraction, the negative x over x squared plus x minus 1. I factor the denominator. You totally know how to do that. You know how to use a quadratic formula, factor it with the roots. And now I'm going to do this thing, this very optimistic thing that you may have learned about in Calc 2 called a partial fractions decomposition. I'm going to be optimistic and say, I bet that I can find some constants a and b so that when I split this weird fraction up into two fractions, when I add them together, remember when I add them together, I've got a common denominator. I'll kind of cross multiply and add. When I do that, I'm going to get exactly this function up here, right? And if you've taken a Calc 2 class, you've done problems like this where you had to clear and there was a little bit of algebra. I actually typed up all the algebra, and it wasn't so bad, but it was a little bit technical. It was a lot bit technical, actually. And so instead, I want to show you what the answer is, right? And so at the end of the day, I kind of wrote it out this way, and I did a little bit more rearranging. But at the end of the day, I got this expression here, right? And if you're someone who likes to see every step, if you want to have everything checked, just pause the video here and just work this out. Get a common denominator on the right-hand side. Plug in R1 and R2. They're these things with square roots. You may have to rationalize the denominators. You may have to do some algebraic simplification. But I promise you, if you do that, you're going to get this thing on the left. So this equal sign really, really, really is true. If you're not going to go and do that, which I frankly don't blame you, let me just convince you that this is true. Remember our lovely graph here, this green thing? That was our function, negative x over x squared plus x minus 1. And I'm claiming that it's the same as this thing down here that was just on our screen. Well, I don't know. Let's see. Oh, look. They seem to be exactly the same. And so a picture is worth 1,000 words, maybe. These graphs literally are 100% the same. And that's just because these fractions are equal. And so I've now, what have I done? Let's see if I've got a summary. Good, good. It's a great place for summary. We have this really long sum, right? Where the coefficient of, this tells me that the fourth Fibonacci number is 3, because it's coefficient of x to the fourth. Tells me the third Fibonacci number is 2. Remember, the nth Fibonacci number is the coefficient of x to the n. And I worked it out. Remember, we did the thing, we multiplied by s and x and did all the subtractions. Did a bunch of algebra. And we found that this whole expression, and indeed this, so therefore this thing, is equal to this thing here, okay? Where we have to tell you what R1 and R2 are, right? Again, I kind of swept that messy algebra under the rug. My apologies for that, but I hope it's still convincing. And now we're ready to use our formula. Remember that formula I told you we would use? I told you anytime we had 1 over 1 minus something, it's equal to 1 plus that something squared, that's something cubed, etc. And so now what am I going to do? I'm going to apply that to this fraction here. And then I'm going to apply it to that fraction there. And then I'm going to subtract because there's a minus sign between them, right? So let's do it, right? We're almost there. We've just shown that our this power series, this infinite sum of our Fibonacci numbers with its coefficients is equal to this thing here, right? And again, I know it's messy. I really wish it was whole numbers. I wish it didn't involve the square root of 5, but it's life. And now I'm going to use that formula. I'm going to take this first fraction, 1 over 1 minus negative r2x. I'm just going to plug it in. It should be 1 plus this squared, plus this cubed, etc. Now I'm going to do the same thing with this second fraction. And you can imagine mathematicians doing this well before computers, well before Desmos, back in the, I don't know, in the 17th century or something like that, working through all of this on paper. And imagine the discovery when they said, oh, now cool, so now I get to subtract all this. I get to subtract 1 plus r1x plus negative r1x squared and carry this through. And then imagine the kind of excitement when they saw the 1 minus a 1. What's that? That's 0. That means that our constant terms cancel. Well, that's pretty doggone good because we don't have a constant term in our power series, right? The first thing we get is an x, right? And then now let's see what we get. We get negative r2 minus a negative r1. Well, that's going to be negative r2 plus r1, and then we divide by square root of 5. If you go back and look at what these numbers were, if you plug that in and simplify, you're going to get exactly of this number 1. Right? And so now we're basically ready for the punchline. And the punchline is that if I work out this, if these really are equal, in math, when we use an equal sign, it means equals. If I ask what's the coefficient of x to the n on the left, right? Well, like the coefficient of x to the 4th is the 4th Fibonacci number. The coefficient of x to the 5th is the 5th Fibonacci number. The exponent of x to the n is the nth Fibonacci number. Right? And so now if I work out and say, what's the coefficient of x to the n on the right? Well, that's got to be the nth Fibonacci number. And so let's do that. And so the nth Fibonacci number, based on what we've done, is going to be the coefficient of x to the n in this expression here. Okay. You may think this is a little bit technical. I don't. I think it's pretty reasonable. And if I'm going to look for x to the n, well, I don't know. Here's x to the 3rd. So x to the n is just going to be, what's going to be the coefficient of x to the n? Well, in the first part, it's going to be negative r2 to the nth power. Okay. And then what's the coefficient of x to the n down here going to be? Well, I guess it would be the term with the nth power. So it'd be negative r1 to the n. I guess I have to subtract them because I've got a minus sign. And I guess I've got to divide by square root of 5 because that was what was in my formula. And so this tells me that the nth Fibonacci number is equal to this formula here. Right? And so now if I go and I just substitute everything in, right? I've literally just copied this and rewrote it a little bit. Oh, there may be a small typo over here. Maybe ignore that. But once you type everything in and you work out what the R1 and R2 are in terms of the square roots, I substituted everything in. And I got this formula, exactly the one that we saw on Wikipedia. Okay. And as you, I guess you can see that we're on the end of the slides page, slide 55. But first of all, I want to thank you for watching to the end of this video. And I just want to offer, just a little summary, right? Where do we start with? Well, we found a sequence that arises in nature and is quite beautiful and simple to describe. We get one term by just adding the 2 previous terms. And we were faced with a question, why does the formula for the nth term, why does it, first of all, why is it exponential? Why does it involve the square root of 5? Why does this work? And we found a reason, right? And if you go back and look at what we did, you may think this is kind of technical, but really, what did we do? We had this cool idea to kind of think about it in terms of a power series. Maybe this gives you a new appreciation for power series, maybe not. And then we used a little bit of algebra. We had to factor the denominator. We used a quadratic formula, right? So we had a clever idea to use some note keeping with exponents. We did this cool trick where we noticed a pattern when we multiply by x, kind of a cool trick with power series. We used a quadratic formula to factor. And then we use partial fractions, which we learned it in a calculus class, but really it's just an algebra technique. Right? And although the calculations were not so bad, but they do involve irrational numbers, they do involve square roots of 5. We were able to kind of break this up and use this formula. Right? This main formula that we proved, right? We proved it by cross multiplying and checking things. And putting that all together, we got this remarkable formula for Fibonacci numbers. And so I hope this maybe shows you that this formula at first seems really out there and maybe where did it come from? But maybe at the end of this, you're saying, oh, It's coming from the roots of a quadratic polynomial and partial fractions and geometric series. And then this is just the tip of the iceberg. And so this technique, this is called the theory of what's called a generating function, can be used to study lots and lots of sequences and find formulas for their nth terms. And if you'd like to learn more about this, please just send me an email. I'd love to chat with you. So thank you so much for watching, and enjoy spring break, which begins now. Have a great day. Bye.